Just now, it's done.
Very good. Okay, so let's move on with the program. So the next speaker is Manuel Rivera from Purdue, and he will speak about the fundamental group of a simplicial cocommutative coalgebra. Please go ahead.
So thank you for the invitation. I'm very happy to see many of you, and I would have really loved to be in Barcelona. Hopefully I can visit at some point during summer and see you in person and discuss some of this in person. So let me state the goals for this talk. Let me first say that all the symbols and terminology in this slide will be defined in more detail throughout my talk. So the first goal is that I want to describe the construction of a functor, which I will call F, from the category of simplicial cocommutative coalgebras. This 0 denotes connected simplicial cocommutative coalgebras. R will be a fixed integral domain during the talk. And I want to describe a functor from simplicial cocommutative coalgebras connected to the category of differential graded bialgebras having the following properties. F will be homotopical in the following sense. It will send a notion of weak equivalence between simplicial cocommutative coalgebras called cobar quasi-isomorphisms to quasi-isomorphisms of DG bialgebras. So cobar quasi-isomorphisms, again, I will define this in detail, but these are maps of simplicial cocommutative bialgebras that after taking normalized chains and then applying the co-associative cobar construction, they induce a quasi-isomorphism. So it's a notion of weak equivalence drawn from Kosul duality of co-associative and associative algebras. So that's the first condition. The second condition is that this construction is modeling algebraically the differential graded bialgebra of chains on the base loop space of a space. More precisely, for any simplicial set with a single vertex, namely reduced simplicial set, there is a natural quasi-isomorphisms of differential graded bialgebras from the differential graded bialgebras obtained by applying F to the simplicial cocommutative coalgebra of chains on X to the singular chains on the space of loops based at B, the base point of X, in the geometric realization of X. So by omega Bx, I mean the topological strictly associative monoid of Moore loops on X based at B. And note that this construction is saying that the quasi-isomorphism type of this differential graded bialgebra can be completely extracted from the simplicial cocommutative coalgebra structure of the chains. Okay, and note also that this should involve some localization step because of course, the zeroth homology of this differential graded bialgebra is a Hopf algebra. Every loop has an inverse up to homotopy, and that inverse map induces a antipode. And on this side, I'm starting with an arbitrary simplicial set, not necessarily a Kahn complex. So the one simplices might not have strict inverses. So this construction should involve a localization step, and I will describe that in detail. And then we can consider this composition of functors. First, apply this functor F from simplicial cocommutative coalgebras to DG bialgebras, then take the zeroth homology of that differential graded bialgebra. We obtain an ordinary bialgebra. Then we can take group-like elements of that bialgebra that will produce a monoid. I don't like the name group-like because it will not be a group if the bialgebra does not satisfy the property of being a Hopf algebra. So maybe we should say monoid-like elements. And then in order to obtain a group, you can just apply ordinary group completion or localization to this monoid to obtain a group. And this composition is what I'm calling the fundamental group of a connected simplicial cocommutative coalgebra. Okay, and for all of our purposes, we can stop here and consider the composition landing in monoids, because for the classes of simplicial cocommutative coalgebras that we will be interested, the resulting monoid will have the property of being a group. Okay, so that's the first goal, to describe this construction and outline the proof of these properties. The second goal of the talk, time permitting, is to use the ingredients that went into the construction of the functor f in order to describe extension of classical results in algebraic topology of Whitehead, Frank Adams regarding the Kohlbar construction, Quillen and Sullivan on rational homotopy theory, Goers on characterizing spaces of Toubal's field localization, and the theory of Mendel regarding characterization of homotopy types in terms of E-infinity algebras and so on, from simply connected spaces to spaces with arbitrary fundamental group. Okay, so again, the constructions used in the functor f will lead to extensions of all these classical results in algebraic topology from nilpotent or simply connected spaces to spaces with arbitrary fundamental group. And this leads to a conjectural path for an algebraic characterization for all homotopy types. Okay, so I will state a conjecture at the end of the talk explaining this point. Okay, so let me start by recalling the notion of a simplicial cocommutative coalgebra. So throughout the talk, R will be a fixed integral domain. There are some points in which certain R modules that I'll be considering, I would have to assume that they are flat. I hope to remember to say when I need this. So a simplicial cocommutative coalgebra C is a simplicial object in the category of cocommutative coalgebras. So that's a functor from the opposite of the ordinal category to the category of cocommutative R coalgebras. These are R modules. These consist of an R module C together with a cocommutative co-associative coproduct, which I will denote by delta, and the co-unit, which I will denote by epsilon. This is equivalent to the data of a sequence of cocommutative coalgebras indexed by the non-negative integers with phase and degeneracy maps satisfying the simplicial identities, and moreover, preserving the coalgebra structures, right? And we will say C is connected, a simplicial cocommutative coalgebra C is connected if C0 is isomorphic to the underlying ring as a coalgebra with coproduct given by sending the unit, determined by sending the unit to the unit tensor the unit. Okay. The main example will be the simplicial cocommutative coalgebra of chains on a reduced simplicial set. So let X be a reduced simplicial set, that is a simplicial set with a single vertex. So all path connected spaces can be modeled in terms of reduced simplicial sets. And by R bracket X, I will denote the simplicial cocommutative connected coalgebra of chains. So in degree n, this is the free R module generated by the n simplices of X, and the coproduct delta n, or each coproduct delta n, is determined by declaring the generators to be group-like. In other words, by defining the coproduct on any generator sigma to be sigma tensor sigma for any sigma in an n simplex, okay, and extend linearly to all of R of xn. there's another functor that I will be using, the normalized chains functor. So given a simplicial cocommutative coalgebra, a connected simplicial cocommutative coalgebra, I can obtain a differential graded coassociative coalgebra. So far, this construction makes sense for non-commutative coassociative simplicial coalgebras, right? So this denotes a category of differential graded connected counital coassociative coalgebras. So let me recall this construction. So the normalized chains first as a differential graded R module is given by a quotient. So first consider the chains, the usual chains construction on the simplicial R module, the underlying simplicial R module. So at Cn, you have curly Cn, and the differential is given by the alternating sum of the face maps. That's a chain complex. And I mod out by degenerate chains, the subcomplex of degenerate chains, those which are images of degeneracies. So, and I get a differential graded R module, a chain complex. Okay? And then the coproducts of C, of the simplicial coalgebra C, induced a coproduct on this differential graded module in using the Alexander-Whitney natural transformation, right? So first you, by naturality, we have a map from the normalized chains on C to the normalized chains on C tensor C, which by C tensor C, I mean degree-wise tensor products, right? And then I apply the Alexander-Whitney natural transformation, sorry, to obtain a map from the normalized chains on C to the normalized chains on C tensor the normalized chains on C. Okay. So as our main example, we have the differential graded coalgebra of normalized simplicial chains on a simplicial set, right? This is a construction that we all know and love. So it's the normalized chains on this simplicial coalgebra. I will denote it by C star of X with coefficients in R with the usual differential. And this is sometimes called the Alexander-Whitney diagonal approximation, right? And this is given, this coproduct can be given more precisely in terms of the following formula. So for any n simplex sigma, the coproduct is given by first restricting sigma to the first I-dimensional face of the simplex sigma, tensored with the last n minus I dimensional face. And then you sum over all I, starting at 0, ending in n. This is the Alexander-Whitney coproduct. And as a remark, we know that this is a differential graded coassociative coalgebra, but it's not strictly cocommutative, right? However, we know that it's cocommutative up to homotopy, and even better, you can construct a natural family of higher homotopies describing the homotopical cocommutativity of this coproduct. In other words, this functor, which I'm calling n star, which lands in differential graded coassociative coalgebras, extends to a functor from simplicial cocommutative coalgebras, I'm assuming connected for now, to E infinity coalgebras, which are connected. And it's given precisely, the E infinity structure can be described precisely in terms of the surjection operad. And these are ideas that started with Steenrod. They were written down by McClure-Smith, Clement Birch, and Fraisse, and so on, right? So there are two notions of weak equivalences, which I want to highlight in the category of simplicial cocommutative coalgebras. So the first one, so first we say a map F of simplicial cocommutative coalgebras is a quasi-isomorphism if the induced map to normalized chains is a quasi-isomorphism, namely it induces an isomorphism on homology. And then there's a stronger notion of weak equivalence, which I'm going to call Kohlbar quasi-isomorphisms. So a map between simplicial cocommutative coalgebras is a Kohlbar quasi-isomorphism if it becomes a quasi-isomorphism of differential graded algebras after applying the Kohlbar functor to the underlying differential graded co-associative coalgebra of the normalized chains. So omega here denotes the Kohlbar functor, which I'm considering from the category of differential graded co-associative connected coalgebras to the category of differential graded algebras. And let me say that this notion, it was not coined by us. It has appeared in the literature in many forms. I think the first appearance in the Lie context was probably Hinich. In Hinich, in the associative context by Lefebvre Hasegawa, and then it was promoted in articles and books of Bruno Valette. Also, Gabriel Drummond Cold and Joey Hirsch have studied model category structures with this notion. So yeah, so note that this notion of a Kohlbar quasi-isomorphism is strictly stronger than quasi-isomorphisms. Okay, any Kohlbar quasi-isomorphism is a quasi-isomorphism, but not vice versa. Okay? They agree when you restrict to the context of simply connected coalgebras. So in the context of rational homotopy theory, for example, these two notions agree. Okay, but once you leave this world of simply connected coalgebras, the notions are not equivalent. Okay. Any questions up to this point? No. Okay, so let me recall the definition of the Kohlbar functor. So, of course, this makes sense in more generality for co-augmented coalgebras. I'm just considering connected coalgebras for now. So the Kohlbar functor denoted by omega. So if C partial delta is a connected differential graded co-associative coalgebra, then the Kohlbar functor is given by the differential graded algebra obtained by taking the free algebra on C bar, where C bar is obtained by shifting C in this way. And TC denotes the free algebra, the tensor algebra on C bar. And tensor denotes the free associative product, so just concatenates non-commutative monomials. And then D, the differential, is given by taking the sum of the differential of the underlying co-associative coalgebra and the coproduct and extending as a derivation to all of TC, right? So you consider, there's a sign here, you consider the sum. This gives a map from C bar to the tensor algebra on C bar, and then you extend as a derivation. And then the fact that d squared equals 0 is equivalent to the differential of the coalgebra squaring to 0, delta being co-associative, and delta and partial and the differential being compatible, namely that the coproduct is a chain map, right? So if we start with a simplicial cocommutative if we start with a connected simplicial cocommutative coalgebra C, again, we can take the normalized chains. That will be a differential graded co-associative coalgebra, which is connected. Then we can take the co-bar construction of that to obtain a differential graded algebra. Oops, it's not connected, I'm sorry. Obtain a differential graded algebra. And it turns out that so there is a well-known construction. The E2 coalgebra structure on the normalized chains induces a differential graded bialgebra structure on the co-bar construction of the normalized chains of C. So a bialgebra is given by a coproduct on the a bialgebra structure on the co-bar construction is given by a coproduct, which is compatible with the product in the sense that the coproduct will be an algebra map. This coproduct will be co-unital, and the units and co-units are also compatible. I will not describe this construction in terms of the formulas in this talk, in terms of the formulas for the E2 structure, but I will describe it in terms of an example later on in the talk, namely for the case when the simplicial cocommutative coalgebra is obtained from taking chains in a space. Okay, and I think once you describe it from here, this informs you how to construct this structure in the algebraic case for simplicial cocommutative coalgebras in general. Okay, so I will describe this structure in this particular case later on in my talk. So in summary, the co-bar construction of the underlying differential graded co-associative coalgebra of the normalized chains on the simplicial cocommutative coalgebra has a natural differential graded bialgebra structure. Okay. Okay, so now let me describe the functor, which I mentioned in the first goal of the talk. So I want to describe a functor from the category of simplicial cocommutative connected coalgebras to the category of differential graded bialgebras. And let me introduce some terminology. So this curly G will be the group-like elements functor from bialgebras, from ordinary bialgebras to monoids. Again, I write quote unquote, because in general, this will not be a group, right? You get a monoid and you get a group if the bialgebra has the property of admitting an antipode, of being a half algebra. So for any bialgebra, this as a set, this monoid is given by all elements G and B, such that the coproduct acts in this diagonal way, and the co-unit at G is 1. So this functor F will be defined as follows. So for any connected simplicial cocommutative coalgebra C, we will consider the co-bar construction of the normalized chains on C. That has a differential graded bialgebra structure. And I'm going to localize a certain set of cycles. Okay, so derived localization is the algebraic counterpart of Dwyer-Kahn localizations. Okay, for differential graded algebras or differential graded categories and so on. So this set PC will be the set of group-like elements in the 0th degree bialgebra of the co-bar construction on the normalized chains of C. Okay, so again, the co-bar construction forms a bialgebra, since I started with a simplicial cocommutative coalgebra. If I look at degree 0, I obtain an associative, co-associative bialgebra there, and I take the group-like elements here. So it's kind of like a way of a natural functorial way of selecting this set of cycles. And I'm going to localize at them in a homotopy invariant way. Okay.
Sorry, Manuel,
So
could I ask a question?
Yeah.
I think you mentioned it just a few seconds ago, but I may have gone over my head. This localization is in the sense of boost field, but I think
No.
that is
Yeah. This localization. I will comment more. I will be more precise in a second.
There's this paper of Chuang and Lazario.
Yeah.
Yeah. I'm forgetting another name.
Chuang, Holstein, and Lazarev. So that's my next slide. Okay. So
apologies. Sorry.
Yeah. There you go. Yeah. So again, this is the algebraic counterpart of Dwyer-Kahn localization, right? So it's a homotopy invariant way of localizing differential graded algebras, or more generally, differential graded categories, right? And it was introduced or described in detail by Brown, Chuang, and Lazarev, and I learned this from them as well. So it goes as follows. So if A is a differential graded algebra and P is a set of cycles in A, we define the derived localization of A at P as a homotopy pushout. So you consider the free algebra generated by P, and you localize strictly the elements of P to obtain this algebra generated by P, in which you add formal inverses, and you have a map into A induced by this inclusion, and you take the homotopy pushout of this diagram in the model category for differential graded algebras, in which a weak equivalence is a quasi-isomorphism and a fibration is a surjection. Okay, and this construction is exactly mimicking Dwyer-Kahn localization in the algebraic context. Okay, and it's designed in a way such that it's invariant. Of course, it's a homotopy pushout. It's invariant under quasi-isomorphisms of differential graded algebras. So let me go back for a second to the definition of F. So a priori, I'm considering this as a differential graded algebra and applying this localization, and I obtain a differential graded algebra. So it's not clear that if you start with a bialgebra, you get a bialgebra structure on this localization. So I want to explain that in terms of a explicit model, explicit functorial model for this derived localization. Okay. Are there any questions? Okay, so let me give you an explicit cofibrant replacement in the case of my P, this set of group-like elements, an explicit cofibrant replacement for this map, functorial. So again, let C be a simplicial cocommutative coalgebra, and I'm going to consider the following simplicial sets. So for all elements in X, for all elements X in PC, remember this PC are the group-like elements on the degree 0 bialgebra structure in this cobart construction, right? So for all of these elements, I'm thinking of these as loops, right? So I'm going to consider a circle just modeled as the simplicial set with one vertex and one non-degenerate, one simplex. I'm going to consider a circle for each element in this PC, and I'm going to take the wedge of all of them. So this is a bouquet of circles, right? So I'm calling that space that simplicial set associated to C. I'm calling it Y of C. And then I'm going to fiber and replace this simplicial set in the category, in the Quillen-Mull category of simplicial sets. I'm going to use this X infinity construction. So I obtain a fiber and replacement, and now I'm going to take chains on this fiber and replacement, followed by cobar to obtain this map. Okay, so this will be a cofibration of differential graded algebras. I homotopically invert all of these loops in the circle, right? All of these circles in the bouquet, homotopically invert them using a fiber and replacement. And then I take chains and then followed by cobar. This can be described algebraically, but I think it's conceptually clear if I describe it in this way. And you have, of course, you have a cofibration like that, and you have a map like that. And now you can take the ordinary push out in this diagram will compute the homotopy push out that we're looking for. And that's what I'm calling this, this LPC of the cobar of the normalized chains of C. Oh, so far, this is a differential graded algebra. Does that make sense? And it's functorial with respect to maps in this category. Functorial with respect to map of simplicial cocommutative coalgebras. Okay. It turns out that there is a natural, again, with respect to maps of simplicial cocommutative coalgebras, bialgebra structure here. And this follows from the universal property of the pushout, since there's a natural bialgebra structure on this corner because it's the cobar on the normalized chains on a space. There's a natural bialgebra structure here. There's also a natural bialgebra structure here. And all of these maps will be maps of bialgebras. And that induces a bialgebra structure on the pushout. Differential graded bialgebra structure. And this is the functor F associated to any C, any simplicial cocommutative coalgebra C. I look at the normalized chains. I take cobar construction, think of that as a bialgebra, and I localize in this way these group-like elements in degree 0 here. And I claim that this is modeling the bialgebra of chains on the base loop space. But it's purely algebraic. I mean, quote unquote, purely algebraic here, right? But this is just a way of describing this construction. So that's F, the map that the functor that associates to any C, to any C this object here. So, and then I define pi1 of C as I promised. For any C, you apply F, you get a differential graded bialgebra, right? Then you take the zeroth homology, you obtain an ordinary bialgebra. You take the group-like elements, you obtain a monoid. And now you group complete to obtain a group. But as I said, for all of our purposes, we can just focus here for now, since the simplicial cocommutative coalgebras that I will be considering here will always produce a group at this stage. That's a Q construction, which produces a group associated to any simplicial cocommutative coalgebra which is connected. And it's homotopical in the following sense. First, F, the functor that sends C to this differential graded bialgebra, is homotopical in the sense that it sends Kohlberg quasi-isomorphisms to quasi-isomorphisms. That's immediate from construction, right? Since this derived localization is designed to be invariant with respect to quasi-isomorphisms of algebras, right? So a Kohlberg quasi-isomorphism is a map of simplicial coalgebras that induces a quasi-isomorphism of algebras after applying the Kohlberg construction. So that's immediate, since the derived localization is invariant with respect to quasi-isomorphisms of algebras. And then this is also immediate, right? That this construction pi1 sends Kohlberg quasi-isomorphisms of simplicial cocommutative coalgebra to isomorphisms of groups. And now I'm going to prove that, or I'm going to outline the proof of the fact that this construction, this algebraic construction, is modeling a construction from topology. Namely, for any reduced simplicial set, the differential graded by algebra f of x is quasi-isomorphic as a bialgebra to the chains on the space of Moore loops in X, in the geometric realization of X, based at B. So this localization step was needed to obtain the homotopy type, the correct homotopy type of the base loop space. Otherwise, I don't have inverses up to homotopy in my model. Okay. So in particular, this means that this capital pi1 of the simplicial cocommutative coalgebra of chains on a simplicial set completely determines the fundamental group of a space. So this is kind of a conceptual point I would like to emphasize, which I at least it was not clear in the literature to me, is that the chains on a simplicial set, the algebraic structure of the chains on a simplicial set, suitably interpreted with the correct notion of weak equivalence, completely determines the fundamental group of a space. Are there any questions up to this point? Okay, so let me outline the proof of this theorem, or kind of describe the history, how I got to understand this fact. So it's based on an extension or a revision of Adams' Kohlberg theorem. Okay, so Adams, I think Adams introduced the Kohlberg construction in 1956 and described the passage from a simply connected space to its base, to the monoid of base loops. Described that passage algebraically in terms of this Kohlberg functor, in terms of the differential graded co-associative coalgebra of chains, right? So we extend this this statement of Adams to all path-connected spaces, possibly non-simply connected, with arbitrary fundamental group. Of course, the subtlety is to consider coalgebras under the correct notion of weak equivalence, right? Which is the one given by this Kosul duality between co-associative and associative algebras. Let me say that in more detail. So I'm going to denote by C star for the next slides the functor of pointed singular chains, I'm calling them. So given a path-connected pointed space, so this 0 is for path-connected, this star is for pointed, I can produce a connected differential graded co-associative coalgebras, a connected differential graded co-associative coalgebra called the pointed singular normalized chains. So given a pointed space y with base point b, I can consider the con complex, which I'm calling sing of y at b, which consists of all simplices with vertices at b. Okay, so that's a reduced con complex. It has a single vertex. I can take I can take the chains on that con complex, right? I'm just writing it in this way, but this is just the singular chains on the space y generated by singular simplices with vertices at b. All right. So that's a connected differential graded coalgebra with coproduct induced by the Alexander-Whitney coproduct. So what do we prove in 2016 together with Zainalian? First, that the singular chains send homotopy equivalence between spaces to this stronger notion of quasi-isomorphisms between coalgebras, namely to Kovar quasi-isomorphisms of coalgebras. Of course, it's essential that I'm using singular chains here. Since this gives me I'm taking a con complex model for the space, right? So I don't have to mention this localization step. So we stated it in this way first for spaces, for con complexes. And moreover, for all pointed spaces y with base point b, there's a natural quasi-isomorphism of differential graded algebras from the Kovar construction of the singular chains on y, the pointed singular chains on y at b, to the chains on the Moore-based loop space at y, the space of Moore loop space at b. There's no hypothesis of, or there's no restriction on the fundamental group of y in this statement. That's why it's extending Adams' classical Kovar theorem. Of course, the proof of Adams does not go through in this case. The spectral sequence proof fails in the, there's a hypothesis that you need to compare spectral sequences, which fails in the non-simply connected space. So you need a different proof that actually uses the fact that you're considering y as a con complex. Any questions? Okay, so here's a proof outline of this extension of Adams' theorem. So for any reduced simplicial set, we will construct a cubical set, a monoidal cubical set, which will model the base loop space. I'm denoting this a monoidal cubical set by, this should be a Gothic C, I think mathfrak C. So mathfrak C cube of X. So this is a monoidal cubical set having the following properties. When I triangulate this monoidal cubical set, I obtain a simplicial monoid, which is naturally isomorphic to the simplicial monoid obtained from X by applying this construction, which is popular in the theory of higher categories. So, so there's this adjunction between simplicial sets and simplicial categories, which is given by, given any simplicial category, there's this homotopy coherent nerve construction of Cordier, right? And then we have the left adjoint, which is denoted by the Gothic C. I think I learned this from Lurie, the explicit description. And this adjunction gives equivalent equivalence between model categories which model infinity categories, right? So you think of of the simplicial sets with the Joyal model structure, simplicial categories with Werner model structure, and then this is a Quillen equivalent. So it lets you compare different models for infinity categories. Okay, so we construct, we note, I should say, we note that this construction of C, this functor C, naturally factors through cubical categories. And there's a subtlety here. I'm lying a little bit because this is not quite a cubical set. You need the notion of cubical sets with connections of Brown and Higgins in order to obtain a functor, in order to obtain a well-defined construction. So the connections appear naturally here, which is kind of amazing. So we construct this cubical set such that after triangulating, you obtain this simplicial monoid. Of course, it's a simplicial monoid because X has one vertex. In general, for a general X, this will be a simplicial category, of course. So you obtain this simplicial monoid, which was already studied in the literature, right? And moreover, the cubical chains on this monoidal cubical set is exactly the Kovar construction of the chains on X up to natural isomorphism on the nose. Okay, so let me kind of describe this monoidal cubical set. And that kind of also uses ideas of Bauss. Bauss had also described cubical sets, modeling loop spaces, and so on in terms of so-called necklaces. So given any X, this cubical set is obtained as follows. So we look at all necklaces inside X. So what's a necklace? So a necklace is a simplicial set obtained as a wedge of simplices in this form, of standard simplices in this form, where the last vertex of one simplex is glued to the first vertex of the next one. So it's an ordered sequence of standard simplices identified in this form. That's a necklace. By a necklace in X, so necklaces form a category with maps being maps of simplicial sets that preserves the first and last vertex. Okay. Now I can consider the over category, the category of necklaces over X. So these are, I think of these as necklaces inside X. And since I'm assuming X has a single vertex, all of these vertices will go to the base point of X. Right? So for every necklace inside X, I consider the cube of the appropriate dimension as this is a standard cube. Maybe in the category of cubical sets with connections, you need that. So you consider that standard cube of the appropriate dimension. This is the same dimension that appears in the Kovar construction, right? The sum of the dimensions of each simplex in this monomial of simplices, this necklace, minus the number of simplices. So you consider that abstract cube, and then you glue all of these according to how these necklaces fit inside X. And that's you obtain a cubical set, which is monoidal, with the product is induced by concatenation of necklaces. So I should also say the names of Duggar and Spivak, which described also this triangulated version of the functor C in terms of necklaces. but there's more data, which is slightly redundant, right? Because now you're taking a cube and you're triangulating. So you have to label all those simplices in the triangulation, right? So this is what we do. We construct, or this is how we got to our model, by understanding this construction of C in more detail, right? We noted that the chains on that cubical monoid is exactly isomorphic to the Kovar construction on the simplicial chains on X. And then what? And then when X is a complex, we prove that the geometric realization of this monoidal cubical set is homotopy equivalent as a topological monoid to the space of loops, of more loops in X base of B. So we work at the space level. When X is a complex, you can construct an explicit homotopy equivalence between these two spaces. So this is a kind of a cubical complex model for the base loop space. So what's the upshot of this? Well, now if I take the zeroth homology of the Kovar algebra, so X is a complex now with a single vertex. So if I take the zeroth homology of the Kovar algebra of the chains, that's exactly the zeroth homology of this guy, which is the zeroth homology of the base loop space, which is, as an algebra right now, is the group algebra of the fundamental group, right? And now for an arbitrary simplicial set X, in order to obtain the right homotopy type, you have to incorporate this localization step, right? If X is not con, then you have to localize localize the DG algebra of chains on X. I'm just assuming X is a simplicial set with a single vertex, a reduced simplicial set. So you localize that that DG algebra, you localize it at this set of cycle. This set of cycles in this particular case will exactly be all paths, right? Considered as generators in the Kovar construction. So you localize at those. And you can show that that's weakly homotopy equivalent to the Kovar construction of the chains on this localization of the simplicial set X at the one skeleton and all the arrows. So this should be interpreted as infinity localization, right? So I'm thinking of X in this construction. I'm thinking of X as an object living as a quasi category, as an object living in the Joyal model structure, and I localize it everywhere in a homotopical way, and that's exactly the same as con replacing X, right? So when I do this step, this derived localization step, that's compatible with the homotopical localization of categories in this way. And then I know that the Kovar construction of the chains on a con complex model the chains on the base loop space. So when X is not a con complex, I localize in this way to get the right homotopy type. Okay, so some comments about history. So this perspective of localizing localizing the one simplices in the Kovar construction. Now the one simplices become 0 degree, the vertices in this Kovar construction, right? 0 degree elements. So this perspective was suggested by the work of Chuang, Holstein, and Lazarev. They revisited our paper in terms of this derived localization, my paper with Mahmoud. which was more from the perspective of infinity, of the quasi-categorical language. And similar constructions also appear in earlier papers of Catherine Hess and Andy Tonks, and also in a paper of Konstevich. So Hess and Tonks and Konstevich, in order to model the base loop space of a simplicial set, they essentially consider the Kobar construction on the chains, and they added strict inverses for all the one simplices in your underlying simplicial set. So they localize strictly. So this was kind of the first appearance of this idea, I would say. And this works because in this context, when you're taking a simplicial set and taking the Kobar construction on the chains, then because of a cofibrancy condition in this context, derived localization can be computed by strict localization. So that was kind of an observation of Chuang, Holstein, and Lazarev, that what they were doing here was homotopically invariant localization. And then I'm saying that this collection of one simplices that I'm localizing can be obtained functorially from the simplicial cocommutative coalgebra structure of the chains. If you consider this as a cocommutative object, then from the bialgebra structure on the Kobar construction, you can obtain this basis that you want to invert by applying a group-like elements function. So it's not extra structure, the elements that you want to invert. They're already completely determined by the simplicial cocommutative coalgebra structure on the chains. So in summary, what we have done is that we have outlined that for any reduced simplicial set, this differential graded bialgebra. Oh, sorry. So far, this identification is as differential graded algebras. I haven't mentioned the why these are compatible as bialgebras. I will do that now in a second. Okay. So are there any questions up to this point? So I have a question. At what time should I stop talking?
Just go ahead until 1:15. That's fine. That's
okay.
15 minutes more.
Okay. So, okay. So the bialgebra structure can be obtained. So I wanted to describe how to. I remember I promised you I would describe the bialgebra structure on the chains, on the Kobar construction of chains, the Kobar construction on the chains of a simplicial set. The bialgebra structure is obtained from a cubical coproduct. So any cubical set, let K be a cubical set, the cubical chains also have just as simplicial chains on a simplicial set, have a natural diagonal approximation, which is given as follows. So for zero simplices, you can define this coproduct to be group-like, the diagonal, for all of these generators. Then for one simplices, you can define it to be the coproduct that given a one cube, it's not one simplices. Given a one cube, you send it to the first endpoint tensor, the one cube itself, plus the one cube itself tensor, the last endpoint. And now this completely determines a coproduct on cubical chains using this nice fact that every cube, any n cube, is a product of one cubes. Okay, so this coproduct was considered by Sir back in the days. This cubical chain approximation for the diagonal. And of course, you can write a formula in terms of shuffles and so on, an explicit formula for this coproduct. So given a simplicial set X, now I can consider the cubical chains on this cubical set, which is isomorphic to the Kohlbar construction. So since I said that the cubical chains on any cubical set have a natural coproduct, I obtain a coproduct in the Kohlbar construction that makes it into a differential graded bialgebra. And then since this is a free algebra, this coproduct is determined by component maps in this way. And then you can go back and relate these component maps to the E2 coalgebra structure of your underlying E infinity coalgebra of simplicial chains in the simplicial set. Okay, so that's a way you could discover this this construction of a bialgebra structure and the Kohlbar construction of an E infinity coalgebra in this way. Anyway, it turns out that if X is con, then this identification becomes a quasi-isomorphism of bialgebras, namely between the Kohlbar construction on the chains of X and the chains on the base loop space. So I should be more pedantic here and write the geometric realization. And as a corollary, you can show that this DG bialgebra obtained by applying the functor f, right, by localizing, agrees or is naturally quasi-isomorphic to the bialgebra structure on the Kohlbar construction on the chains of this Kant complex. Okay. And then this implies that pi 1, this capital pi 1 of this simplicial cocommutative coalgebra, again, which was defined as first applying f, then zeros homology, then group-like elements, is the same as applying the group-like elements to the zeros homology bialgebra of the chains on the base loop space. Sorry, zeros homology bialgebra of the base loop space. And that's exactly a fundamental group. Namely, once I have the bialgebra structure, that completely determines the underlying group through the group-like elements function. So it's in this sense that the simplicial cocommutative coalgebra of chains completely determines the fundamental group of a space. Consider under this notion of Kohlbar quasi-isomorphisms. Great, so some applications of this construction. So we study complete invariance for spaces up to the notion of pi 1 R equivalence. So what's a pi 1 R equivalence? So a map of reduced simplicial sets f from x to x prime is called a pi 1 R equivalence if f induces an isomorphism on fundamental groups and f induces a R homology equivalence between the universal covers. That's a pi 1 R equivalence. And we want to study complete invariance for spaces up to pi 1 R equivalence. So first note that a pi 1 Z equivalence is the same as a weak homotopy equivalence of spaces. So spaces up to pi 1 Z equivalents are just homotopy types, right? Isomorphism on fundamental groups and homology integral homology isomorphisms on the universal cover. These are simply connected. So by Whitehead's theorem, these are isomorphism on homotopy on all homotopy groups. The notion of a pi 1 rational equivalence is equivalent to a map that induces a isomorphism on fundamental groups and an isomorphism on all higher rationalized homotopy groups. So this is capturing more than the Malsev completion of the fundamental group and the nilpotent case and so on. I'm trying to capture all of the fundamental group. Okay, and in general, you can show it's a easy exercise that a pi 1 R equivalence is an R homology equivalence, but not vice versa. Okay, so a first application is the following extension of a theorem of Whitehead. So, which was proven in collaboration with Felix Wierstra and Mahmoud Zainalian. So let X and Y be two reduced Kant complexes, then a map F between X and Y is a pi1 R equivalence if and only if the induced map at the level of coalgebras of chains is a Kovar quasi-isomorphism. So this is, I mean, this is pretty cool. Like, what happens when R is Z? The integers. A map is a weak homotopy equivalence if and only if the induced map between integral differential graded coalgebras of chains is a Kovar quasi-isomorphism. So Whitehead's theorem is this statement for simply connected spaces and replacing Kovar quasi-isomorphism with quasi-isomorphism. Right? And we obtain a stronger statement over a field, which is the following. Let F be a field, and this extends the theorem of Goers, which Goers proved extending the rational homotopy theory of Quillen and Sullivan to arbitrary fields. So let F be a field, then two reduced Kant complexes X and Y are homotopy. There's a mistake here. So I should say are pi1 R equivalent, sorry, F equivalent, are pi1 F equivalent if and only if the connected simplicial cocommutative coalgebras of chains, Fx and F of y, are Kovar quasi-isomorphic. So note that I dropped the existence of a map from this theorem. So this is a complete invariant for spaces up to pi1 F equivalent when F is a field. The cocommutative coalgebras of chains. Okay, and let me quickly recall Goers' theorem, how this extended Goers' theorem, and I will try to say something about the proof about our extension. So Goers proved that if X and Y are simplicial sets, then and F is a field, then the simplicial cocommutative coalgebras of chains are quasi-isomorphic if and only if X and Y are F equivalent, meaning an F equivalence is a map between spaces or simplicial sets that induces a F homology equivalence. Okay, so these are complete invariants of spaces when considered up to quasi-isomorphism for spaces up to F equivalence, up to this Bausfield F equivalence of spaces, right? And the idea of Goers was to use the derived functor of points, which I'm calling RP. So any simplicial cocommutative coalgebra gives you a simplicial set just by taking the group-like elements, quote unquote groups, because now it will just be a set at every degree. That will give you a simplicial set. And then Goers derives this functor. He constructs a model category structure on simplicial cocommutative coalgebras, which is suitable to derive this functor and obtain the following theorem. He proved that first, when F is algebraically closed, then the map from X to the functor of points applied to the simplicial cocommutative coalgebra of chains is exactly the F localization of X, namely the fibrant replacement of X in this Bausfield model category of spaces up to F equivalence, which I'm calling LF of X, when F is algebraically closed. And then for any arbitrary F, he proved that the localization at F of a space X is weakly homotopy equivalent to the localization at its at the algebraic closure of F, and that's how he obtains this statement. Okay, this statement up here is for any field F. So simplicial cocommutative coalgebras characterize spaces in this sense up to F equivalence. And we strengthen this notion of equivalence to capture the fundamental group and the F and the localization, the F localization of the universal cover. Okay, so I think I'm going to stop here, and let me state. I can say more about the proof if anyone wants of our theorem. It involves some nice constructions. For example, we construct the universal cover of a simplicial cocommutative coalgebra algebraically, which models in terms of simplicial cocommutative coalgebras the construction of the universal cover that uses the fundamental group of a simplicial cocommutative coalgebra. And yeah, we use that construction, and that's part of a more general theory of simplicial twisting cochains, a theory of simplicial twisting cochains, and so on. In any case, the conjecture I want to end with is a conjectural kind of a path that we have opened a path for an algebraic characterization of homotopy types. Now we have shown that for any field, we can characterize spaces up to pi1 F equivalence by means of simplicial cocommutative F coalgebras. So now the idea is to use arithmetic square arguments to conclude the following. So this is a conjecture. So for any two reduced Kahn complexes X and Y, then the following are equivalent. So X and Y are homotopy equivalent if and only if the integral simplicial cocommutative coalgebras of chains are Kobar quasi-isomorphic in the category of simplicial cocommutative coalgebras. If and only if the singular chains, or the simplicial chains on these Kahn complexes are Kobar quasi-isomorphic as E-infinity coalgebras. So this would extend in several ways results of Mendel, which are in terms of E-infinity algebras of cochains for nilpotent finite type spaces. So the idea is that strengthening the notion of weak equivalence between algebraic objects using ideas from Koszul duality, you can capture the fundamental group in complete generality, as well as the homotopy type of the universal cover, right? And I think that's all I'm going to say today. Thank you for listening.
Thank you very much, Manuel. Oh, are there questions or comments?
I have a couple of questions, if I may ask.
Yes, who's speaking?
One is very naive.
I
think that, yeah, it works.
Let me stop the sharing.
Yeah. Okay. Yeah, one is a very obvious thing. You probably can state some of your results and conjectures in terms of equivalences of categories, or maybe equivalent equivalences just by rewarding. Is it true? Or
there are subtleties. This has to do with, for example, considering fields which are algebraically closed. So, in order to so the answer is not quite. I think you would need to consider more structure. For example, the theorem of Mendel, which characterizes simply connected spaces in terms of the E-infinity algebras of cochains. That construction is not fully faithful. Okay, it is when you consider, but it's good enough to distinguish spaces in this completely distinguished spaces in this sense. But in terms of obtaining a equivalent equivalence of homotopy theories, I think you might need more structure.
Okay, and then the other one is just a comment, because earlier at the beginning, by the beginning of your talk, you mentioned the fact that you apply a homotopical localization to something as an algebra and then automatically localize it as a bialgebra. And you have an ad hoc proof of that. I mean, this is a situation which sounds very familiar. In fact, it's already mentioned in that paper of Brown, Chuang, Lazarev, and this is a situation that we also found it quite often with Andy Tongs and Oriol Raventos. And it's the following, that the homotopical localizations always gives you more, preserves more structure that you would expect. So a typical example is that you take an algebra in any context where it makes sense, you localize it as a module, and then suddenly what you obtain happens to be automatically an algebra, and it happens also to be a localization in the category of algebras.
Right.
This is a phenomenon that you can usually prove in very general grounds, and you don't need to do specific constructions to obtain that. Just I wanted to mention it.
I see. I did it in this way explicitly with this particular functorial replacement, because I think I don't have a good grasp on the homotopy theory of bialgebras. I think I need to understand that better. Yeah.
Very interesting. Thank you very much.
More questions?
Can I make a couple of comments?
Yes.
Yeah.
So, I mean, there's this nice phrase about mathematicians. They always like to tell other mathematicians, well, what you really mean is this. So I'd like to thank you for telling me what I really meant with my paper with Catherine. That was a really nice talk. I now know what I should have said. Yeah, yeah. So now, second question, you probably know where the second question is coming from. Is there a Kahn loop group functor hidden in the things you're doing? Is that
Yeah. Can I take 2 minutes? Let's see. So, yeah. So there's this construction. So this is also amazing, actually, that I recently understood, and I think you will appreciate it. So,
Manuel, are we seeing
your screen again? Yeah.
Your screen?
Let me quickly share it. How do I do that? I go like here and start. I'm glad you asked. Actually, I wanted to tell you this.
Me too.
So I described this simplicial monoid associated to any x, right? Which is obtained by applying this left adjoint of this homotopy coherent nerve functor. So this is more generally a simplicial category if x has many objects. Okay. So what's amazing is that there are two things you could do. I mean, you can localize everything strictly, just degree by degree, to obtain a simplicial groupoid. Right? You can localize everything. That's fibrant. It's a simplicial groupoid, right? You can only localize the one skeleton. I'm going to call it x1 of x. That's not a simplicial groupoid, but you have localized everything that you need to in order to obtain the right homotopy type, considering this as an infinity category, because then you can fibrant replace the higher things in the infinity categorical way. So my first point is that these two things are weak equivalent as infinity categories. So as like Dwyer-Kahn equivalents, right? Dwyer-Kahn weakly equivalent. Okay. Dwyer-Kahn weakly equivalent. So the philosophy is that I'm thinking of a space as a infinity category in which all arrows are invertible up to homotopy. That's the philosophy. And then I play around with combinatorial models for these infinity categories and the passage between simplicial sets and simplicial categories. Okay, so this is the first observation. Second observation is there is a natural map, which I'm going to call, and I'm doing this for you, the Sharba map at the space level. This is the Kahn loop group of X. And this Sharba map at the space level is a weak equivalent, a Dwyer-Kahn weak equivalence. So after taking chains here, I obtain a quasi-isomorphism between the chains on a Kahn loop group and the chains here, which are naturally quasi-isomorphic to the Kohlberg construction. I mean, you just have like more simplices, remember, because this is the triangulation of that thing. But it's essentially the same thing. So that's what's going on. There are three ways of this to describe a space in this model category of, I should say, like the Berner model category, right? As an infinity category. All you want to make sure is that your one simplices are inverted, right? In this model structure to obtain that the homotopy category is a groupoid.
Yeah, I guess Clemensberg also knows this stuff. I mean,
yeah,
that's what he started with in his work.
I see. Yeah. I've had conversations with Clement as well recently. Very informative.
Perhaps I can make a comment.
Yes,
Here.
who's speaking?
Clemens.
Joachim.
Ah, I see. I don't see you. Okay, hi.
Yeah, so
Oh, there you go.
what I did actually in my thesis was not exactly what you are describing here, but I constructed a bigger model, a prismatic model of the loop space, and
Right.
I embedded Kahn's loop model into this model, and
So
also
there's a fourth thing.
yeah, and
maybe.
also Bauer's model, both.
I see.
And I somehow realized by accident that Bauer's model embeds into Kant's Kant's model. So if you triangulate Bauer's model, then you can embed it into Kant's model. And I somehow conjectured that you get precisely Kant's model if you invert, make it into a group. That's what you are telling here.
Yeah, I see. You know if that map that you get after triangulating is exactly the Sharba map?
This I do not know, because I do not very well know the Sharba map.
It's amazing that it's a map, I think, from the 40s or something.
Yeah,
right? A paper from the 40s. So
Yes.
But it is not a simplicial map. It is rather a kind of twisting.
Yeah, twisting
chain or something like that.
Right, but the point is that you can put all of these together to obtain a simplicial map. In that way.
But what is very interesting is that this prismatic model, I didn't realize that, but it is precisely, it's very much related to what you said with the necklaces. I realized that Bauer's model simplicity subdivided, so triangulated, is precisely this necklaces. So this is written down in my thesis and is also published. So somehow, but very condensed. So it's not, perhaps not explicit.
Is your thesis online now, Clemens? The complete thesis?
Yes,
I've read the paper.
Also on my webpage. On my webpage too.
It's there.
And so what is the thing? which has probably to do with Sharba, is that in this prismatic, the Kahn model has a universal property. It is the universal twisting. So you have a twisting function from X to the Kahn model. But it is initial in the set of all twisting functions.
I see.
And so whenever you have a twisting functions from X to a simplicial group, you have a canonical function from the Kahn model into your simplicial group.
I see. Yeah.
And therefore, I just constructed such a twisting function for omega x, which is very geometric. And this gives you the map from gx into omega x, which is it's mysterious. You don't really understand it. This is just by universal property.
I see.
The construction of Bowers, when you triangulate the construction of Bowers, this is very geometric. You can really understand what it means. And therefore I have a very explicit embedding of Bowers model triangulated into omega x, and I just checked by hand that it factors through the image of Kant's model.
I see. But it's interesting is also that Cordier in this homotopy coherent nerve was also considering the same constructions.
Yes, but actually this is related to some kind of duality. You see, somehow it is related to another fact. If the simplicial set and you forget the degeneracies, and you realize it as a semi-simplicial set, then actually you get something which is much bigger.
The fat thing, yeah.
A fat realization. And this fat realization, you can also realize it as a cubical realization.
Oh.
And somehow this is related to all this.
I see. Cool.
So, but
Thank you for the comments.
Thanks a lot, Clemens, for being here and for your interesting comments and illuminating reflections.
Yes, thank you.
I thank you for organizing. It's marvelous.
Oh, thanks. It's a pleasure to organize such a thing. And also thanks to Daniel, who is speaking next, because he has agreed to give us more time if we need it, but I think that maybe we don't need it after all, right? Well, we may need some rest, but we may dispense with it, right? And just proceed to Daniel's talk.
Yes.
Whatever you think is best, I'm happy with. So
Yeah, it's up to Joachim.
Let's thank Manuel again.
Thank you for listening and for the invitation. I hope to see you, some of you in Barcelona.
Yes, because I there were more questions, I'm sure. I mean, I had some, but
I want to discuss this with you all in person.
Absolutely.
Okay, so I stop the recording here, Joachim?
Yes, but then you can immediately start the next one, please.